start recording and start the introduction. So thank you all for attending this Applied PDE seminar. We haven't had so many this quarter, but this one is going to be a good one. This is a talk by Raphael Stuhlmeier. This is, I think this is the third talk I'll be attending by Raphael, and I have to say that I've been very impressed with the other two. Raphael is clearly an outstanding speaker, so I think we'll all learn something today. Raphael did his PhD with Adrian Constantine at University of Vienna, and I think after that he was a postdoc at the Technion, is that right?
Yes, that's right. No,
and for a few years now he's been at Plymouth, and he's going to talk to us about the instability and evolution of inhomogeneous broad-banded seas. Thank you, Raphael.
Well, thank you very much for the introduction, and thank you for the opportunity to speak here in this very interesting venue as well. So the title is a bit of a mouthful, and I want to break this down into essentially three parts. And I want to start really with basics. I want to start with linear theory and the concept of an energy density spectrum. And I want to try to convince you, without doing, let's say, going into too many of the details, why this is interesting and why it's important. And then I want to build up a little bit of nonlinear wave-wave interaction theory. And then in the third part of the talk, that's really where the things that are, the words that I'm using in the title are going to start to be relevant. I want to try to apply this nonlinear theory to stochastic evolution equations. So to try to say something about how the energy density spectrum changes with time. And then in particular, to try to convince you that the problem of whether broad spectra are stable or unstable to disturbances is interesting. And well, I still haven't resolved this problem. I don't think that anybody has resolved it, but I think there's a lot of interesting work being done in the area right now. So it's really an area of very active interest. So without further ado, I think let's just jump into the Euler equations. And now, I don't know the backgrounds of everybody here in the room, so I thought I would write down the linear water wave problem first. And my view of water waves is that we have incompressible Euler as the kind of model for really for water waves that makes the most sense. It's the model that's most accessible. And in particular, because you get to avoid a lot of the difficulties of the Navier-Stokes equations. So I've assumed here that the fluid is irrotational, which means that I can write my governing equations in terms of a velocity potential phi. And in the linearized problem, so I have this free surface variable that I'm going to call eta, and the entire problem is posed on a strip, so that the fluid domain, this wavy domain between the bed at -h and the surface, which is now in the linear problem posed at 0, actually boils down to solving the Laplace equation in a strip. Now, it seems like there are 4 equations here. Actually, we can eliminate one equation. We can eliminate eta from the system entirely, and we just get an equation in phi. And that's essentially the standpoint that was taken by, say, George Green in the 1830s. So the linear finite depth theory was more or less solved in the 1830s. Not to say that all of the applications of that theory were really fully explored until quite a bit later. But this is the problem that I want to start with.
Raphael, I have a question.
Yes.
You say the problem was solved in the 1830s. Do you mean the problem on the whole line or with periodic boundary conditions? How about if you had the problem with boundary conditions?
Okay. The problem for periodic waves. So let's say, okay. Now, okay. The problem for periodic waves was solved by George Green, I think, in 1836.
Yeah.
Now, okay, there are. You can think of many other scenarios. In particular, I haven't specified whether the bottom boundary is now I'm assuming that it's fixed, and I'm assuming that it's not, doesn't move in time, that it's not, doesn't vary in space, and that it's just a constant. But of course, if you were to vary the bottom boundary, now suddenly the problem gets much, much richer, and you can start to see a lot more physics, and certainly things that George Green wouldn't have been doing. So, but thank you for the question. So, the solution that I want to concentrate on is the periodic wave solution. So linear progressive waves in unidirectional have a form that looks like this, where the free surface is a sinusoid. I have some amplitude A, and the potential, okay, so we have another sinusoid, and then we have the vertical eigenfunctions of the Laplacian here. And I really only want to look at two properties that we get fairly easily from the linear theory. The one is that we have a relationship between omega and k, the dispersion relation for finite depth, such that the frequency, so omega squared, is g being the force of gravity, k the wave number, and times the hyperbolic tangent of kh. And for the linear problem, the important thing for what's going to come is that the energy is equipartitioned among potential and kinetic energies, and in particular that it's proportional to a squared. So the energy is proportional to essentially the amplitude squared, or if you like, the average, so time average of the free surface elevation squared. Okay, so it's very classical, and it's what you would find in any textbook about water waves. Now, of course, one wave is nice, and it's easy to write down. But if you look at the sea, you see that there are waves of all different kinds of frequencies that occur. And I've just put it, so this is, of course, there's a lot more occurring here. You see this is an active wind sea. There's white capping and other things that I really can't talk about. But there are certainly lots of components. So there are big undulations of fairly long wavelengths, and then there are lots and lots of smaller components everywhere. So to describe a sea, you clearly need many, many different modes. But what you also need is not just this deterministic standpoint that we've been taking here, but actually to have all of the information about these modes is overkill in the sense that it doesn't make sense to talk about wave after wave, which wave is coming at time right now, and then a second later, which modes are arriving, and so on and so forth. What's much more interesting is to try to get a handle on average quantities of the sea. So that's what's interesting for engineering design, and those are the quantities that are going to be more or less constant in. So if you have linear theory, and you don't have any dissipation, you don't have any input by the wind, then you're going to have, as we'll see in this stochastic viewpoint, you're going to have a statistically steady state. And the route that I want to take is I want to say what it makes sense to do practically is to view the surface not deterministically, wave after wave after wave, but as a stochastic process. And here I've taken out the x dependence just to write things a little bit more compactly. So I just have a sinusoidal waves here, and my underline here means that I'm thinking of these as random variables, and eta of t is a stochastic process that depends on time. And practically, what's interesting about this is that we can look at the spectrum of the stochastic process. So just like you would in signal processing, and essentially in any other application, looking at the Fourier transform of the autocorrelation of this process, or if you want to speak a little bit more loosely, at the variance of the sea surface elevation. And this spectrum allows you to calculate important characteristics of the sea state. So in particular, you know that, for example, 4 times the square root of the total variance is going to give you significant wave height, and you can extract information that you need for an engineering analysis. So the spectrum takes this mess, this chaos of the free surface, and it compacts it into a specific shape. And for example, a shape that looks like this. And you can see on the vertical axis here, we have, say, a variance density. So if I multiply by rho and g, I get an energy density. And here I have frequency. And this shape, which incidentally is empirical. So all spectral shapes that we have, like the Pearson-Moskovitz spectrum or John-Swap spectrum, all of these just come from empirical measurements. And there's no clear derivation from first principles of what this kind of spectral shape should look like. You know a lot about certain parts of it, but because the spectrum is a kind of balance between all kinds of forces, between wind and dissipation, and as we'll see later also between nonlinear interaction, essentially all of the shapes that we have for how energy is distributed in the sea come from measurements. And here, so okay, we have a peak, for example, here that happens to be at a 5-second period, and we can integrate over the spectrum, and we can find, for example, total energy content. We can see that this is associated with a significant wave height of 1 meter, and so on. Now, okay, in the title, we said something about broad spectra, and I just want to give you an idea what I mean by that. If I have an infinitesimally narrow spectrum, that's monochromatic sea. There's only one frequency. There isn't energy anywhere else. And as the spectrum broadens, I get energy first close by, close around my, close to my peak frequency. So I get something like a slowly modulated wave train. And as the spectrum broadens even further, we start to see a sea state that has many, many frequency components in it. So a broad spectrum is something that you could think of as characterizing an active wind sea. So in a stormy region, there's wind forcing on the sea, and you see waves of many, many different frequencies. Now, there's something else that I haven't mentioned explicitly yet, and maybe you've been anticipating it. I said the spectra that we have, that we as a community have, that we have in ocean engineering, they're all empirical. So they come from measurements. And in particular, I want to make a simple point with this map of winds over the Western Mediterranean. In order to measure wave heights for a spectrum, so energy distribution, I need to put an instrument in the sea, and I need to let it record for a given time. And then I need to average those recordings. Now, of course, I'm going to need several instruments. So say I have an instrument here and I have an instrument here. And you see the wind is coming off. This is about the border between France and Italy right here. So if I'm recording over the same time period, it doesn't make sense for me to measure or to take a measurement here and average it with a measurement here. Because there's 50 kilometers, say, of fetch that this wind has been generating waves over, that there's no wind here. So it's almost trivial to say, when you do measurements, when you try to measure a spectrum, the conditions need to be homogeneous in space, and in particular, they also need to be stationary in time. Stationary in time means that if I start measuring now, and I want to average a time series, then it's no good if 5 minutes into my measurement, suddenly a squall, enters my measurement area, or boats drive past. So I need statistical homogeneity and stationarity for spectra to make sense, formally speaking. And so just to show you how I'd envision that, if I think of my free surface elevation as a stochastic process, I have many, many realizations of that process. So here's one realization, which happens to be now as a time series, and another realization, and another, and so on, k realizations. If we're talking about time, then usually we use the word stationarity, and space is usually associated with homogeneity, but people have different conventions, so maybe for you, homogeneity covers all of them, but I've put both of them here to make that hopefully as clear as possible. So stationarity for this process eta means that if I take my first order average, if I take a mean here and I take a mean here, that mean has to be the same. So the mean cannot change depending on where I measure in the time series. So if I'm ensemble averaging. And it also means for higher order moments, so if I take a covariance between, so these 2 points, expected value of eta k of t0 and eta k of t, or sorry, eta of t0 and eta of t0 plus tau, that needs to be the same as if I take that here at these 2 points. So the statistics can only depend on separation, so the separation in my time series, okay, only on this variable tau. That was implicit in my description of the spectrum, because otherwise the Fourier transform, well, here, Fourier transform of the autocorrelation only makes sense if the autocorrelation only depends on tau. Otherwise, if it depends on T1 and T2, well then, okay, which variable am I taking a Fourier transform? So this is, it's physically it makes perfect sense, and you need to do this to have sensible measurements, and it's also always in the background when we talk about spectra mathematically or statistically. Okay, so now I've given a brief introduction to what a spectrum is, but of course a spectrum is a single characterization for now not an unchanging C per se, but a statistically unchanging C, in the sense that, okay, each realization might have a different sequence of high and low waves, but statistically speaking, all of these realizations will have the same properties. But we know that the sea or waves, if you go to the beach and you look out, I mean, everything is constantly changing. There's motion, you have the Euler equations, you have, of course, wind input and dissipation. In this picture, there's quite a lot of dissipation, although I won't talk about wind input. I will talk about the Euler equations, because the Euler equations, in fact, are nonlinear, as we all know. So here's the full set of the Euler equations. And I've written them again in a potential formulation. And now in the second part of the talk, I want to try to explore what ramifications that nonlinearity has for, essentially, for how waves interact. Now in linear theory, okay, you have any waves and they superpose. In nonlinear theory, well, okay, you have the Euler equations. And it's difficult to extract from those equations a sense of what's going on when there are several waves in the sea. So rather than going into the equations themselves, I want to give a very simple kind of overview example in the style of Whittam, or if you look in the book. I mean, this is if we start with a linear dispersive operator, such that we have either only even numbers or odd numbers of x and t terms, say on the left-hand side. L of u equals 0. This has some plane wave solutions, and okay, we have a real dispersion relation omega of k. And now I can superpose as many of those as I like. There's still solutions. Nothing happens. If I have a quadratic nonlinearity on the right-hand side, and on the left side, I can still superpose solutions. And now, okay, I'm thinking to be more candid. My viewpoint is the weakly nonlinear, and I've put it here in the title. I haven't made that explicit. Maybe I should make it explicit. My viewpoint is the weakly nonlinear perspective, such that I can say that this is something like a small perturbation to the linear operator over here. And okay, what I'm leaving out is that in this weakly nonlinear perspective, the amplitudes also need to depend on time and so on. But okay, this is just for the overview. So where I have a superposition on the left-hand side, on the right side, I have products of this superposition, which will give rise to terms like this, the terms that we have on the right-hand side here. And now, when is this interesting? When is something happening? Well, I have a linear oscillator on the left side, and I have some kind of forcing like this on the right side. And now this is this gives you something when the frequency of the forcing coincides with the frequency of the oscillator if you're in simple harmonic motion, or in this case, if the frequencies and wave numbers on the left side, so for a free wave, coincide with those that you find on the right side. So this is a resonance condition. And you see that a triad, so 3 waves in resonance, a triad resonance condition arises from quadratic nonlinearities. Now, if I have a cubic nonlinearity here, I've just changed the right side. Okay, I can superpose, say, 3 waves, and those are going to give me products of 3 terms. And again, what's the interesting case? The interesting case is a quartet. So for 3rd order, I'm going to start to have interactions between 4 waves. So on the face of it, it looks like, wow, okay, there's lots and lots of interactions. We have all kinds of plus and minus signs and this and that and the other. But what we need to bear in mind is that this problem here has a specific relationship between the frequency and the wave number. So if I take quadratic and cubic nonlinearities, as I would if I were doing perturbation expansions in the Euler equation, say, I'd get quadratic and cubic and quartic and so on, and if I were very patient, I would get whatever order I wanted. Well, in deep water, and I'm just going to use deep water from now on, in deep water, there is a relationship between the frequency and the wave number. That means that I need to satisfy this condition here for triad resonance and this condition here for quartet resonance. And it turns out that this specific dispersion relation means I don't have any triad resonance. There isn't any resonance at 2nd order. And in fact, I only have quartet resonance for certain specific signs. So if there's a K1 plus K2 minus K3 minus K4 and these signs right here. You can see, if you remember the dispersion relation for general water depth, now if you're in shallow water, omega I is Ki square root of GH. So omega is directly proportional to K. So you see in shallow water, everything resonates. You get resonance even at quadratic order. In deep water, okay, you need to go to a higher order, which makes things, in some sense, a little bit more technical. Okay. Now we've seen this for this kind of schematic example. In the Euler equations, the first ramifications of this kind of resonance, this kind of interaction between waves, was seen by Stokes in 1847. Stokes did a cubic expansion, so expansion up to 3rd order of the Euler equations in deep water, and found that at 3rd order you start to get corrections in the frequency. You don't get corrections in potential up to 4th order in deep water and so on, but okay. So what Stokes was essentially observing is that a wave interacts with itself at this cubic order and has this, you see some kind of effects from a wave interacting with itself. And it took a long time. It took until the late 50s and then for TIC to do the same thing for 2 wave trains in up to 2nd order. And in principle, you could think about doing a perturbation expansion. But I want to cut that short. Oh, I'm sorry. Okay. Okay, I should say a little bit more about quartet interactions. So I've shown you this this picture in a schematic, and I want to convince you just that, okay, this isn't just a mathematical abstraction. This kind of interaction, which here, and I'm taking a picture from Phillips in 1960, who was the first person. Then TIC in 1959 went to did 2 wave trains up to 2nd order. Phillips was yet more patient with his algebra and did 3 wave trains up to 3rd order, and was able to find that due to the shape of the dispersion relation, you find resonances on these kinds of curves. And actually very shortly thereafter, interestingly enough, Longet-Higgins and then Phillips separately in a second paper only 2 years later actually found these things in the laboratory. So if you're in the lab and you generate waves of a certain wave number, a certain frequency. And so they have to be just right to fulfill your resonance conditions. And here I'm showing you, for example, a triad or a degenerate quartet, which is two waves where one of them is counted twice. So say this wave 3 is composed of two waves of, a wave 3 that's half this wave vector and another half of this wave vector. So if you have this kind of a triad and you generate two waves at one end of a wave tank and you let them interact, you can actually see the third wave that's generated by this nonlinear interaction, and that was seen in the 1960s. So this isn't this isn't just a mathematical abstraction. This is something that very quickly people realized, okay, it's a mechanism that's very important in what's happening in the sea. Now, rather than doing perturbation expansions, I want to skip ahead a few years, historically speaking, to the reduced Zakharov equation, which takes just essentially a Fourier analysis perspective and says, okay, instead of looking at one wave or two wave or three waves, I'm just going to take a continuum of waves from the get-go. So the Zakharov equation arises from a Fourier transform of the water wave problem that's rewritten in terms of variables at the free surface, taken to third order, then non-resonant terms are eliminated. So multiple scales ansatz in this equation is a compatibility condition for no secular terms to arise in that multiple scales ansatz. So with that said, just a few, let's try to unravel what's going on here. I've got T2 here, which is a slow time scale proportional to epsilon squared times a physical time, which comes from the multiple scales ansatz. On the right-hand side here, I see that I have a cubic nonlinearity. It's exactly what I need for deep water quartet resonance. I have a delta function, a Dirac delta, over the wave numbers, which tells me that I need to be an exact wave number resonance. And I have this kind of term, so this is exponential term over the frequencies, which tells me that if I'm close to exact frequency resonance, so if this is close to 0, that's where I'm going to have the biggest contributions. This is going to be slowly varying, or most slowly varying, close to where these frequencies are close to 0. So the biggest contributions are going to come from the vicinity of resonance, but the Zakharov equation essentially lets in terms that are near resonant as well. We'll see how that's important later on. The structure of this equation is almost universal, and really the information about the water wave problem is contained in this kernel, this T0, 1, 2, 3, where all subscripts, so equations tend to get a little bit big. So subscripts are always going to denote wave number components, so that, for example, B subscript 1 is B of wave number K1, and so on. This is omega of wave number K1.
Quick question.
Yes.
Is the T in the exponential there T subscript 2, and
Yes.
and also the capital B dependence, is that also a T subscript 2 dependence?
Thank you. This is unfortunately a typo in the slide. Yes, this is all the same time scale.
Okay.
It's all T2. Yeah.
And the capital T in your scaling is the original physical time?
Yes, this is original physical time.
Okay.
So thank you for that. So this kernel encodes all of the information of the third order water wave problem with the non-resonant terms and bound modes eliminated. Okay, so these are the two ingredients that haven't come into this reduced Zakharov equation. Now, okay, I want to show you that using this equation, we can recover a lot of known results. So you can get, for example, the Stokes frequency correction. If you assume that this complex amplitude B, which, okay, you can see here how it relates to the Fourier transform of the free surface and the Fourier transform of the potential at the free surface. But if you assume that there's only one wave in the sea, now you need to integrate to get rid of one of these delta distributions, the Zakharov equation takes a very simple form. And in particular, we have a simplified expression, I mean, essentially one line for this kernel T0000, which is that this is K0 cubed divided by 4 pi squared. And you find that the solutions are, they're solutions of constant amplitude B, and inverting this canonical transformation, you get back the free surface elevation eta, which you see is essentially our sinusoid with the third order frequency correction term right here. So that's Stokes correction. And you can recover a lot of really, I mean, results that take a lot of work if you just use perturbation expansions from the Zakharov equation, because that work is in there, it's in the kernel. So the kernel also simplifies if there are only 2 wave trains. So for example, Longet, Higgins, and Phillips together have a work on the mutual interaction of 2 wave trains in a C. So how is the frequency shifted by one wave train in the presence of another? Now we know Stokes says frequency is shifted, or the frequency of one wave, its self-interaction leads to a frequency shift, but also 2 waves lead to a mutual phase correction or mutual frequency correction, where this essentially just plugging in these 2 waves into the Zakharov equation, simplifying the kernel, gets you these expressions. And you see that a long wave has a much larger effect on a short wave than vice versa in terms of a mutual interaction. And finally, maybe most importantly, if you assume all of the energy is concentrated around a single mode, so there's a single wave number K0, and you replace the kernel by the kernel for that wave number, meaning K0 cubed over 4 pi squared. You do a Taylor expansion of the frequency about that wave number. That allows you to invert the Fourier transform here and to rewrite this simplified system in terms of an envelope amplitude. And this was the endpoint of Zakharov's analysis in 1968. The reduced Zakharov equation was an intermediate step, if you like. But the reduced Zakharov equation is a mother equation of the nonlinear Schrödinger equation, if you assume that you're in narrow bandwidth. So, and that's going to be important going forward. Okay, so I hope I've convinced you that there's some interesting stuff going on in the nonlinear theory. Probably nobody needs convincing, especially nobody in this audience. But now let's try to combine this. I've tried to motivate a linear stochastic description. Now I've said, well, okay, actually there are nonlinear effects. How do those impact the stochastic description? And the stochastic description works on the level of an energy density spectrum. Energy density spectrum is related to the Fourier transform of the autocorrelation. So what we want to look at is a correlation function. Now what we're working with a deterministic equation, and I should say there's some philosophy involved in what I'm doing. And the philosophy is as follows. I believe that if you give me all of the initial conditions precisely, my subsequent evolution is determined entirely by some deterministic equation that I know, like the Zakharov equation, NLS, or something else, whatever your favorite equation is. But if I don't have all of the initial conditions, so if you give me a realization, I can evolve deterministically. There are no stochastic forcing events. There's no, there are no stochastic sinks or sources of any kind. But I don't know all of the initial conditions. I don't know all of the phases necessarily. Maybe I don't know all of the amplitudes precisely. So let's assume that my variable, so the variable b in the of interest in my deterministic description is itself a stochastic process. So the correlation function I'll write as RNM, which again is subscript for Kn, Km. And formally speaking, what I mean by that is this autocorrelation B star. And I'll usually write that in a shorthand without the explicit dependence on Kn and T here. So I'll write that in this shorthand, just to keep things on one slide. So what can we do? Well, if I assume that my deterministic evolution to third order is given by the Zakharov equation, now I can use linearity of expected values to say this autocorrelation evolves, well, according to how each of these correlators evolves. And now d by dt of bn, well, that I use the Zakharov equation. I plug in the Zakharov equation and another one here because the expected value is linear. Okay, now I've got an equation, but what about this guy here? I have an equation for what happens with the second order correlator. Now I've got a fourth order correlator. Well, I can play the game again. The fourth order correlator evolves, well, okay. Linear. I'm sorry?
I have a question on the previous slide.
Yes.
Yeah, so right there, when you substituted in for the Zakharov equation, you're now substituting in with a discrete number of modes?
Okay, I'm substituting a discretized Zakharov equation, yes. So I could do the same thing. So for a discrete Zakharov equation, essentially what I do is assume that the complex amplitude, I'll go back to the Zakharov equation. I assume that this complex amplitude here is a sum of deltas, just like we did for the Stokes wave, and those are the modes that we work with. So okay. Yes, and the reason that I use the discretized formulation now is because later on I want to talk about computations, and the computations are going to work in the discretized formulation.
So if you start with the discretized Zakharov equation for the time evolution for the dynamics, would you get coupled vector NLS or?
So well, it's an interesting question. Now, I don't think that there would be an additional coupling in the NLS, honestly, because the main so the main driver behind the derivation of the NLS is the fact that all of your modes are centered around one single mode.
Right.
So in the discretized formulation, you would have to in place of these integrals here, you would have sums over three wave number components, and you'd have a Kronecker delta in place of the Dirac delta. I mean, just doing it very loosely. You could still invert the Fourier transforms, but I don't think that you would get. You wouldn't get a system of NLS equations.
You're going to get more than a single NLS equation because you're set. I mean, you have more than one wave number.
In the NLS, you also have more than one wave number, but they're all clustered around a central wave number.
Correct. Which is not what you have necessarily.
I'm sorry?
Which is not what you have in a discrete Zakharov equation.
No, not necessarily. So you could think about having several modes and having energy concentrated about several modes and putting that into the Zakharov equation and then trying to do an expansion into getting multiple NLS equations.
Right. That's good.
And I think actually that this has been done by Onorato and co-workers in 2007 to get systems of coupled NLS equations for crossing seas. But it's this is a specific kind of discretization where you really assume that you have energy concentrated about, say, wave number K0 and wave number K1.
Okay.
Yeah. But okay, maybe we'll come back to this afterwards.
Sure.
If you don't. No.
Thank you.
Okay. Well, thank you for the question. So yes, I've discretized the Zakharov equation and I've put that into this formulation. And what I see for my evolution, the evolution of my autocorrelations, is that I get from a second order average here, I get an equation that involves a fourth order average. And for the fourth order average, I get an equation that involves a sixth order average. Here again, I've done a transformation that takes out, so I've transformed the Zakharov equation slightly into a non-autonomous form. So system is now non-autonomous. But so clearly, this is something that's never going to end. We need to put a stop to this hierarchy, and we do that by finding first off that, okay, if we assume without loss of generality, I'm going to say that the process is zero mean. We always have a decomposition of higher order averages into products of lower order averages plus something that we call cumulates. And in particular, if the process is Gaussian, we know that only two moments determine a Gaussian distribution. So the cumulants are all zero. The fourth order cumulant here is zero. All higher order cumulants are zero. So for Gaussian processes, all of the decompositions work very nicely. I can decompose the sixth order average into products of second order averages, the fourth order average into these products with a zero cumulant, and so on. So I close the hierarchy. And in exactly the same way that's been done in physics, say, for the last 70 or 80 years. So this is, in physics, this would be associated, say, with the BBGKY hierarchy. Yeah. And this closure allows us to construct evolution equations starting at order r squared, starting at d by dt of r. My autocorrelation is something in terms of r squared. Okay, so I want to show you a few of these evolution equations. The most well-known by far is Hasselmann's kinetic equation, where you need to assume near Gaussianity to have some kind of closure. And then Hasselmann, in the 1960s, deriving this equation, said, let me also assume homogeneity. Because the evolution of a spectrum, so a spectrum by itself corresponds to a homogeneous C state. The evolution also requires that you have statistical homogeneity, and homogeneity now is measured in Fourier space. So we're in physical space, we say that the statistics at, say, 2 points have to be the same, are only dependent on the separation of the points. In Fourier space, that means that any two modes are uncorrelated. So this is a way, so this is a Kronecker delta in the discretized formulation. This is how you would impose homogeneity. I only have a correlator if n is equal to m. And in addition, you need a somewhat technical assumption that this product of these correlators, essentially Cn is my energy. The product of the energies varies slowly. And if you use our hierarchy of equations, you find at lowest order, you get nothing. You go to an order higher, and then you get, with these three assumptions, you get the kinetic equation. Kinetic equation now is on a very slow time scale, T4. And I have a delta over the wave numbers and a delta over the frequency. So I'm in exact resonance. T4 is something that if my wave slope is 0.1 and my typical period is 10 seconds, T4 is about 27 hours. So it's a very slow evolution of the spectrum where I assume the C state is completely homogeneous. In the last 10 or 15 years, there have been a number of attempts at making do without some of these assumptions. If you don't assume this slow variation right here, you actually find that you get a system of two equations that people have called the generalized kinetic equation. See what evolves on a faster time scale, and there isn't that delta over the frequency. So we have nearly resonant interactions that contribute. So that's important because the kinetic equation and I'll just move back one slide. So the kinetic equation, this equation right here, is essentially what's implemented in all wave forecasting software nowadays. So this is what takes care of nonlinear wave-wave interaction in wave forecasting software. But if you study the structure of the equation, you find, for example, unidirectional waves have no evolution. There's no evolution due to nearly resonant waves. So you can't capture, for example, something like a stochastic analog of the Benjamin-Fair instability, because that depends on near resonance. So it's very interesting to try to get equations that are on a faster time scale that do capture this near resonance. And in particular, it's also interesting to see what happens if you try to get rid of some other assumptions. In particular, what can you get rid? Gaussianity or near Gaussianity is very difficult to get rid of because you need the closure. But the kinetic and generalized kinetic equation are the equations that describe how a spectrum evolves in the absence of anything else. Homogeneity, however, is something that if you get rid of homogeneity, you can start to ask questions like, how does the spectrum evolve if there are small perturbations that involve a correlation between modes? So I'll just show you briefly a schematic of some things that have been done. Here, this is our deterministic framework, Zakharov equation, and down here we have narrowband equations like NLS. On this side, I have, if I make homogeneous assumptions, so I'm statistically homogeneous, I get the kinetic equation, and Longet-Higgins in '76 looked at a narrowband kind of kinetic equation, which gets rid of the kernel. So that's actually quite nice. But what if you allow for inhomogeneity? And there have been two attempts to look at that so far, one by Crawford, Safman, and Yen, and the slightly earlier one by Alber. I want to talk first about Alber's approach, and then I want to tell you about Crawford, Safman, and Yen's equation. And essentially what they did in 1981 was to reduce their equation to Alber's equation and then to reproduce more or less Alber's results. But I think there's more to be said about the Crawford, Safman, Yen equation, and that's sort of the end point. Hopefully in the next 5 or 10 minutes, we'll be getting to seeing how this Crawford, Safman, Yen equation can be used to look at the stability of spectra. So what did Alber do? Alber started with NLS. So actually with 2D NLS, but okay, it's and assumed quasi-Gaussianity, but spatial inhomogeneity. So inhomogeneity, in this case, he's in physical space. So he has an X dependence in the correlators, and he gets an equation like this that I won't go into detail about. But the important result that Alber found is that if you allow for small inhomogeneous perturbations to a Gaussian spectrum, that's what Alber studied, and this is the figure that we see here. If I have a Gaussian spectrum, and this is non-dimensional spectral width, and this is the wave number, so the non-dimensional disturbance wave number. If the spectrum is broad enough, then it's stable to disturbances. Or alternatively, if the disturbance wave number is large enough, then it's also stable. And the reason that I think that this is a little bit unsatisfying is because NLS is derived as a narrowband equation. So you say, okay, if my spectrum is broad enough, then everything is stable. But wait a second, you're starting with a narrowband equation. And you know, for example, if you just look at the deterministic problem, growth rates so instability growth rates for a uniform wave train, so this is, say, from Yen and Lake, 1981. For the NLS, you get an unbounded region of growth rates here. So a uniform wave train is unstable to perturbations for essentially an arbitrarily large wave number, which is unphysical. If you do the same thing for the Zakharov equation, you find this classical instability horn where the growth, so that the instability growth rates are bounded. You get, they're very close to the curve of exact resonance, so this Phillips figure of 8 right here. So the Zakharov, this mother equation of the NLS, gives you better results for the deterministic theory. So it makes sense to look at it for the stochastic theory as well. And in the last few minutes, now, okay, hopefully there's been a lot of preamble, but in the last few minutes, I want to show you a little bit about how that looks. So I start with a discretized Zakharov equation. And again, I look at my autocorrelators. And now, in contrast to the kinetic equation, I get something at low order. I get something at order r squared, which is this equation. So this is essentially the equation of Crawford, Saffman, and Yen in a discretized formulation. I have some conserved quantities and so on. I'm related to wave action and momentum. But I have this equation, and what I can do, instead of going to narrow bandwidth like Crawford, Saffman, and Yen did, I can look at stability for this equation, writing my correlators, so decomposing them into homogeneous and inhomogeneous terms. The subscripts here now denote inhomogeneous or homogeneous. And I see at lowest order, nothing happens to the homogeneous terms. That's kinetic theory tells me at this order, for purely homogeneous theory, there's no change. For the inhomogeneous terms, I get an equation that looks like this, again at lowest order. And the nice thing is that I have the inhomogeneity, and then I have some coefficients that depend on the homogeneous terms. So that depend, and the homogeneous terms are essentially initial conditions. If somebody gives you a spectral shape, a Gaussian spectrum, say, that gives you all of the homogeneous initial conditions. So what you've got now, for the inhomogeneous terms to lowest order, is a matrix system. You can write this whole thing as d r inhomogeneous by dt is a ri, where a, this matrix of coefficients, just contains the homogeneous terms, the initial conditions. So you've got n squared minus n ODEs, and you can look at eigenvalues for this system. And I'll show you the simplest possible case, because this is the case that's graphically as easiest to do, and it's you can think a little bit about classifying. I mean, the more modes you have, of course, the messier the system gets, and the less you can, well, the more difficult it is to say things. So the simplest possible case that makes sense is a degenerate quartet where I have a wave Ka plus Ka again, plus Kb and Kc, and by rescaling, I can reduce that whole thing actually just to two parameters, p and q. So Ka is 1, 0, I have 1 plus pq, 1 minus p minus q. And if I rewrite my Crawford-Saffman-Yen system for this degenerate quartet, I have a system, okay, it looks a bit ugly. I've just highlighted the inhomogeneous terms. So here, all of the red terms are inhomogeneous. I have a system of 6 equations, 3 for the homogeneous, 3 for the inhomogeneous. And now I can actually carry out this linear stability analysis fairly easily. I mean, you can do it on paper if you want. You need to specify initial conditions, and that's where the variation is. Different initial conditions will give you different evolutions for the system right here. So if I specify initial conditions such that I have some correlation here between phases in, say, mode A and mode B, where I have initially small inhomogeneity mu, then I can put that in and I can compute. Where do I have disturbances that will grow? So, for example, for 3 wave slopes here, here's the curve of exact resonance, so Phillips figure of 8 right here in P and Q space. And again, here these are Ka, Kb, and Kc. And I see that I have a whole region of instability right here. And if you specify different wave slopes, you get different regions of instability. And I know, okay, I'll try and sum things up. Why is this interesting? Well, it's interesting because any point where in this region of instability is going to give rise to some kind of evolution, where according to the purely homogeneous theory, I'd have no change on this fast time scale. I would just have these values would go on until my time scale T4 of the kinetic equation. But because of a small inhomogeneous disturbance within my instability region, I start to get evolution. I start to get energy exchange. so here's one numerical computation, there's another numerical computation. So sometimes you get things that look a little bit recurrent, very much akin to Alber's equation. And you can actually relate what's happening in our correlators to the energy of the wave field. Inverting the complex amplitudes for the Zakharov equation, we see the energy of the wave field, or sorry, the free surface elevation is related to the correlators and the complex conjugates in this form. And the energy, well, that's essentially the variance of the free surface. And you can compute that. You compute that the energy is just consists of these terms, RAA, BB, CC, AB, AC, and BC. Here's the homogeneous ones, and here's the inhomogeneous ones, where I have spatial periodicity, but I have time evolution according to this Crawford-Saffmannian equation. Okay, so each of the time evolutions gives you a fluctuation of the wave energy in space and time, starting from a homogeneous background wave field here, that's this green area, and then in space and time, the wave field, the energy of the wave field starts to fluctuate. And so you can get something that looks like this. And of course, if you were interested, you could look at the fluctuations of this energy. You could plot a cumulative distribution function. You can get an empirical probability density function out of it. And you can use these, and now, okay, this is a bit of a, you can use these to look at probability of encounter of waves of a certain height. And here, okay, I've plotted this is a Rayleigh distribution in blue that you would get just from purely homogeneous theory. And here are two cases of evolution with inhomogeneous disturbances. Now, okay, I've put impact on rogue wave statistics here. It's a bit of a sham. Why? Because this is a wave field with 3 waves. So what's a rogue wave? There aren't really many modes. But if you had many more modes, the same kind of procedure would give you an opportunity to look at realistic rogue waves. So exceedance probability so this here is a rogue wave of twice significant wave height. This is h over h RMS 0, and this is 3 times significant wave height. So you see that there's a significant difference. So okay, I think I'm out of time, and I just want to summarize a little bit. What have we looked at? I've tried to convince you, maybe through a circuitous route, that there's value in looking at this Crawford-Saffmannian equation because it evolves on a fast time scale. It doesn't make this assumption that the wave field is strictly homogeneous, and it allows us to incorporate things like unidirectional wave evolution, so statistical evolution for unidirectional wave fields. We don't have a narrow bandwidth restriction like we would with Alber's equation. So there's a lot to be done with this equation, I think. But a lot of questions remain open, including, so I've put up here, classifying all of these behaviors, looking at many more modes, and so on. But thank you very much for your attention, and I think that should be it from me.
So we've already had a lot of questions, but are there any other ones? So I have another one. So you said the last bit about the rogue waves was a little bit of a sham. So I mean, to some extent, everything you've done is weakly nonlinear, right?
Yes, it's all weakly nonlinear, absolutely.
Right, and so then the question is also whether, given the amplitudes that we're talking about with rogue waves, whether they fit into that framework.
Oh, okay. A very, very good question. So, formally speaking, probably not. But then I think stretching the boundary, so weakly nonlinear theory, as of course you know, it tends to be applicable even where it, strictly speaking, shouldn't be applicable.
Sure. Yeah.
So I think a case might be made for it, but I can't tell you with mathematical precision how strong a case.
So in other words, if the model produces good results, then you say C, and if the model doesn't produce good results, then you say, well, it wasn't supposed to in the first place.
Well, okay, this is it's a very opportunistic kind of attitude.
Well, we do this all the time, right?
Sure. But so I would say it's clear that the purely homogeneous theory that's based on a Gaussian C drastically underestimates rogue wave statistics. And there have been a number of, certain, let's say, I think it's fair to say that certain parts of the rogue wave community have looked for mechanisms like nonlinear interaction via NLS as a possible reason for more rogue waves than you would get from Gaussian theory. Now, okay, I know rogue waves is a very, very active topic, and I'm only peripherally involved in this, and there are other things as well that you can get into bound modes, you can get into other things like this that may be equally important. But I think if you were to look at rogue waves from an NLS perspective, say via Alber's equation, then it also makes sense to look at rogue waves from the Zakharov equation perspective, or this Crawford-Safmanian equation.
Oh, yeah,
so
I completely agree.
Any other questions?
Do you want to see if Camille from CRU has any questions? Okay, so apparently there's no more questions. Thank you very much for a very interesting talk. So let's thank the speaker again.
So